Yeah, which the homework is uploaded. If you guys have any questions, obviously reach out to me through email or meet me through office hours. You can come early before class.
It's homework 6, right?
Homework 6, yeah.
One question that was on the test homework, I had to like look up a whole lot about it. The plastic section part
Yeah.
of this. I didn't see anything about that in the notes. Is that when you divide the cross section when top and bottom area is equal, and then it's just the moment with respect to that axis?
Yeah.
What?
So I think because I forgot that, I'm probably going to make that a bonus problem.
Okay.
Because I'm noticing, I think I forgot to talk about that. It was in the PowerPoint slides, I think, or it was just, I know for a fact it's in the textbook, so I'll probably just make that a bonus problem and not count that towards like the major grading, since again, it would kind of be unfair to ask you guys a question relating to something that I clearly didn't talk about in class.
Okay.
So
Are you going to talk about it, or like can you just get like a brief description of what?
I'm going to upload a solution which is going to explain everything that goes on, but the main concept is basically what you see on the right-hand side over here, where basically up in the top corner here for the stress distributions, this would be our conventional yielding profile or our conventional stress profile. And then as the material yields, right, for axial loading, all the material in the cross section would yield exactly at the same time. But because we're dealing with bending, it yields at different locations. It starts at the extreme fibers, top and bottom, and then as you apply more and more load, it becomes more rectangular because the stress can't exceed the yield stress. Until you get that point that's at the very bottom right here, which is basically just full yielding, which is what you were talking about with the area of the top having to equal the area of the bottom. And the reason for that is because when you do some of the forces break down to stress times area, but the stresses have to equal each other. So because of that, you get that the areas have to equal each other.
Okay.
So that's where it mathematically basically comes from. If you were able to get that and able to work on it in the homework, awesome. That's extra credit. But if not, I'm not going to grade your homeworks based on that.
Okay.
All right. So I'm not going to wait any longer since obviously it's 5:06 and there's a few students still not here. So I guess they'll just come in. But basically, this is just an example of a frame that I wanted to kind of show you guys how we would basically work through this. So just to simplify the steps, I'm going to show you guys what the exact reaction forces are. So the reaction forces for this problem specifically, you guys have analyzed frames, like done it in statics, right? You break it up at the hinge and then you analyze it in two separate bodies. So because of that, by doing that, you would find that the reaction force here is actually just that force P, and then there's no horizontal reactions. So matter of fact, there's no reaction actually at that node right there. And the reason for that is because this full force here is directly in line with this force here. So it simplifies the problem quite a bit. Now what makes this complicated is the geometry and the fact that now there's two dimensions associated with it instead of just one dimension, right? So this is where that reference fiber methodology that I was talking about last class really comes in handy. Because for beams, you might be wondering why even bother with the reference fiber. For frames, you want that because then it helps you understand how the structure actually behaves as an entire global unit. So for this problem, I specifically made the reference fibers basically follow this path. Let me just make sure it's all right. Yes. And then last reference fiber was here. It looks a little weird. You could assign it however you want, just as long as the forces with respect to the reference fiber geometry is correct. And that's what we discussed last class. So the first step with solving any type of these frame problems is you basically just, again, like with the beams, cut sections, all right? Now, here's the trick with this problem is what do we use? Where do we cut the section, right? It becomes very complicated. So I generally like to start out wherever your most easiest points are. In this case, I'm going to start off with cutting a section directly through here. All right, so if we cut a section just exactly through there, what we're left with, oh, this is not going to erase now. Okay. All right. So let's cut a section directly through FE. This is going to look a little bit like chicken scratch, so please bear with me. All right, but as we cut a section through FE, we're going to have a section cut right there. Our reference fiber is going to look just like that. We have our force P. This dimension here is going to be dimension X. And then what we need to do is assign our positive sign convention for shear and moment for this force body diagram. All right, in this case, because the reference fiber is on the bottom, draw the shear force going directly towards the fiber. So that's V. Draw a moment going clockwise. And then the last thing, which is unique to frames and not necessarily beams, is with frames, you can also have axial loading. All right. So from the force equilibrium, we could do sum of the forces in X equals 0. And simply enough, we find that there's no axial force carried by member FE. From forces in the y direction, however, we get negative P minus V equals 0, which indicates that the shear force in member FE has to equal negative P. And then lastly, from sum of the moments about the cut, set that equal to 0, M minus P times X, and we get that a bending moment of Px is obtained. Keep in mind that the moment, shear, and axial force are all functions of X. I'm just not writing it because I'm too lazy to keep writing the parentheses X, all right? Now, for my recommendation is to add little subscripts to all of these. So you can call this N, FE, V, FE, and M, FE for simplicity. All right. Now that's the equation for just section FE. What about section EC now? This is where things get a little complicated. Remember the rules about cutting sections throughout the throughout any type of structure? Remember method of sections for trusses. When you cut a section, you draw everything either to the left or to the right. So you draw everything on one side of the section or the other. So for section EC, you need to draw everything to either the left or the right, or in this case, top or bottom. Everything to either side of the section. So for EC, our force body diagram becomes this. And because our reference fiber looks like that, again, draw shear going to the left towards the reference fiber. moment going towards the causing a positive force in the reference fiber, and then your axial force. Don't forget about your force P. But now, what's our function going to look like? Yeah.
Is that when you have a value for the axial load and it's going to be negative P?
Exactly. So, but what I'm guessing I'm asking is all of our equations, we know that this dimension here is dimension L, right? Which means that all of our equations that we develop are going to be with respect to this equation, which we can call y. Right, and then from here, it's like you said, from sum of the forces in y equals 0, we have negative p minus n, which means that the axial force in members EC is negative p, which tells us that member EC is undergoing some type of compression. From forces in the x direction equals 0, we just have negative v, which means that the shear force in member EC is actually 0. And then from some of the moments about the cut equals 0, we have m minus or plus PL. I'm just going to write it up here, which tells us that the bending moment in member EC is equal to negative PL. Do you guys notice anything about the function? Yeah.
It's a constant.
It's going to be a constant. So you'll see that in the diagram that the moment has to be a constant value and that there's no shear force, which again, you know is correct because the shear force is directly related to the moment. We learned that the moment is the integral of the shear force diagram. All right. Now we're at an impasse. Which direction do we go?
We go left because it continues on with the reference fiber.
See, that's the fun of it. It doesn't matter which direction you go. You can choose, just as long as your internal force diagrams are correct, right? So if you were to cut a section CD, then what you would need to do is analyze the entire system looking like this. Or just cut this out and analyze the forces with everything to the left. What do you think is easier, analyzing everything to the left or to the right?
I'll do it right.
To the right. So let's look at CD now. We have our reference fiber. We have our cut. Our shear force for this sign convention is not as simple as down clockwise like the previous ones. What was the positive sign convention for a configuration like this? The shear force had to go up or down.
It would go up since it's on the left, right?
Exactly. And then which direction was the moment?
It would be clockwise because it's always in tension to the fiber.
Exactly. And then your axial force N. Now, what did I say previously about that reaction D for this problem specifically?
There's zero force.
There's no force in it, which means that MCD, no bending moment, VCD, no shear force, NCD, no axial force. It's a zero force member. All right. Now from here, let's go to BC. We analyze everything not to that cut, but to here. Analyze everything to either the left or to the right. So that would either be, look at everything like this, where this is our reference fiber. This is our force P. We draw our shear force going towards the positive sign convention, towards the reference fiber. It looks a little weird, but if you think about it, rotate the page 180 degrees and just flip it, and you'll see that it's basically the cut is on the right-hand side with respect to the orientation of the reference fiber. It's a bit confusing, so sometimes you just need to like rotate the pages around and just follow accordingly. And then the moment, positive-wise, would be this way, so it would be counterclockwise. And then, again, we have our axial force. We know that this dimension here is L, this dimension here is L, and then this dimension here is X, which means that the location of the force with respect to the cut is L minus X. From forces in the y direction equals 0, we get that V for member BC minus P equals 0, which means that the shear force is positive P. From the forces in the x direction equals 0, we just get that the axial force in member BC is 0. And then from some of the moments about the cut equals 0, we get that it should be P times x minus L plus M, which means that the bending moment in BC is equal to P times L minus X. Nope, I'm not X minus L. Correct me on that. This is L minus X, which would make this X minus L. My bad. Please make that correction. Now this is important because from our external equilibrium, when we account for the hinge, as long as everything that has been done properly is correct, the moment at the hinge should be 0. And the reason for that is because the hinge allows for free rotation, which means it can't resist rotational force, which is why the moment is 0. Have you guys heard of the difference between a shear and a moment connection before? It's something that's commonly used in civil engineering structures. Moment resisting frames would be like a cantilever system. Basically, there's no rotation at the end, which means that a full moment is provided. So cantilever beam. If you had a pin and roller, those would be a shear connection. So it's the difference between pin and roller or a simple cantilever. So in this case, because the hinge is there, it's basically acting as a pin roller where it allows for free rotation. Any questions so far?
The roller connection is the shear.
Roller connection would be another type of shear connection where the only translation of shear is vertically or in whatever direction it's supporting the load. The pin can obviously support shear in both x and y directions. So in this case, a hinge would technically translate forces in x and y. But yeah, so it just translates forces, but it allows rotation. All right. Last step is just analyze the internal forces in member AB. So for AB, we cut a section. We can either cut it and analyze everything above the cut or everything below the cut. Below the cut, I think, is a nice and simple thing. So just cut it like that. Our reference fiber is right here. Draw shear force going to the reference fiber. Moment causes tension, and then axial force here. We have a force P, and simply enough, we should get the moment in AB is equal to 0, the shear in AB is equal to 0, but the moment in AB from forces in the y direction is equal to negative P. Now, I don't expect you guys to be able to do this on an exam, because, again, we just spent the last 20 minutes solving this problem. It's a very long and lengthy process, but it's basically like solving 5 beam problems all in one problem. So it is on your homework, though. All right? And then the very last step, I promise, for solving any of these frame problems is just drawing the shear and moment diagrams accordingly. All right. So for the shear force and moment diagrams, remember all of the equations that we had previously developed. So what you'll have is actually an axial, a shear, and a moment diagram. So let me create those. All right. What was the axial force in member FE? Zero. So we'll just label that 0. What about the axial force in EC?
Negative P.
All right. So our axial force is going to look like this with value negative P. What about CD?
0.
BC?
Also 0.
And then AB.
Negative P.
And that's the axial force diagram for frame. I'll give you guys a minute just to sketch it out if you want to. Let me know when I'm good to proceed. Yeah.
When you're drawing obviously the diagrams, is there like a convention as to which side of the frame should be positive and negative?
As long as you clearly indicate which reference fiber, generally I'll just denote positive, negative, and then clearly indicate the reference fibers. I know Professor Dr. Chelly over at Stony Brook, who taught me this method, he's very distinct about which side the shear force and moment diagrams are. That's why I always work with like colors and make sure that the sign conventions are clearly indicated, just to avoid any type of confusion.
Okay, so you just denote like if it's above or below the reference fiber, whether it's positive or negative, and you just follow that convention, correct?
Yes.
Okay.
Mm-hmm. And then once we start getting into like deflections and deformations, you'll notice that the bending moment diagram and shear force diagrams will actually help you with figuring out how the structure actually deforms. And so I will usually draw a deformed shape just to show how the structure is supposed to deform.
Okay.
All right. Now for shear force diagrams. What was the shear force in member FE?
Negative P.
All right. So negative P. The shear force in member EC.
0.
Shear force in member CD.
Also
BC.
positive P.
My OCD is like going through the roof right now. So, oh wait, no, that's right. Let me change these to like just be black, just for my own sanity's sake. So that's 0, 4, 0, 4, 0, 4. This is supposed to be positive P. These were 0, 0, and then this positive P. So this is what I'm talking about, like with the coloring and such. And then what was the shear force in AB?
0.
All right. Last is the moment. What was the bending moment in FE?
Negative px.
Negative px. All right. Which means that the bending moment varies linearly from 0 to x. So we know that the bending moment is going to be 0 at this point here because our x was defined with respect to point F. And then it increases all the way to what length? L. So our bending moment is linear. So the maximum bending moment is negative PL. Here's the nice thing is what's the bending moment in EC?
Negative pl.
Exactly. So it was consistent at negative PL. That's a sign that we know we did it correct because the moment is shared at the joints. Whenever there's no hinge, the moment is always the same at the joints or they sum up together somehow. All right. This was M equal to negative P times X for 0, which is less than or equal to X, which is less than or equal to L. And then for bending moment BC.
P times x minus L.
Mm-hmm. So it started out here and then decreased to 0. Which this would be negative PL, and then this bending moment is equal to negative P times X, P times X minus L. For 0, which is less than or equal to X, which is less than or equal to L. Now, the equations are dependent on the direction that you went. So, whenever you write out the equations, my recommendation is just draw the coordinate in which X is from. So X for that went that way, and X for that went this way. So this was XFE, and this was XBC. And those are the internal force diagrams for a frame. Some frames are much more complicated than this. Some frames are simpler than this. It all just depends on the geometry, the type of loading. If I had put a point load at F going to the right, your shear and moment diagrams would look entirely differently. Any questions about frames at all? No? Everyone understand? Feeling comfortable? Awesome. All right. So, continuing on, I had previously mentioned about the relationship between shear and moment diagrams, but previously I had basically just said that the shear and the bending moment were related through integration. So the shear force V is just equal to the slope of the bending moment with respect to X, and that the bending moment is just equal to the integration of V with respect to X from 0 to L. something. I just want to make sure that I captured everything on this slide. So, what does this ultimately mean? It means that the area underneath the shear force diagram is equal to the bending moment up to that point. We had previously done an example with some of the previous problems, but here's a good example of what we might see on a somewhat more complicated loading scheme. So we can use the geometry of the shear force diagrams in order to draw out the bending moment diagrams instead of having to cut sections each and every single time to analyze the internal forces, because as you guys have seen, it can take some time when you keep cutting sections over and over and over again. So let's rotate this 45 degrees. There we go. And we'll draw a line for the shear force and a line for the bending moment. So what we first want to do, like any other problem, is determine our external reactions. We're going to have an AY and a DY, and then because there's no forces applied in the X direction, we will not have any X reaction forces. So can you guys really quickly calculate what the reaction forces would be? My phone does not want to behave today.